Yeah, thank you. It was a great honor to be here. So today I will, well, this is time series workshop, but when Jian approached me for the talk, I say, oh, probably I don't have anything to talk about time series. Well, I did time series in the past, but that was 3 years ago. I don't want to talk anything 3 years ago. I do have a lot of things related to temporal data. So I offer, say, let me talk about one project we are doing now, part at Simon Fraser University, my research team, and part at Huawei Technology. Okay. So this is about graph. So to motivate why we need to do graph, well, this is a very simple question. I can ask all the audience to think about that for just 1 or 2 seconds. Okay, can you name one thing you are interested in, but that thing doesn't involve in any relation? If you think about this question for just 1 second or 2, you will realize it is very hard to give such an example, right? And to some extent, you are interested in one thing. You are more interested in the relations this entity is involved in. So just imagine when you have billions of nodes, they are connected. Well, we see this in the past, like a social media. So this is the size of different types of social media, okay? And we know they are large. But one question is, well, in this world, we have only several billion people. And for social media, if I have one person as a node and we only have several billion nodes, do we need really a scale larger than multiple billion? But the IoT thing, the Internet of Things, extends the scale dramatically. We are now having the vision and having the ambition to connect everything in the world, to share the information. So to give you just some numbers to start with, in 2015, we already have over 15 billion devices connected. And by 2020, the number of connected devices will be over 40 billion, which is a huge number. And not only those entities are connected, more importantly, updates are conducted in a lightning speed. At Facebook, every day there are over 300 million photos uploaded. And every minute, over 500,000 comments are posted, and over 250,000 status are updated. So you can see the updates are so consistent and so everlasting. Now, the technical challenge is really how to manage and remotely monitor millions of deployed IoT devices in the network, okay? And the application scenarios include the Internet of Cars. For example, like by 2020, I just mentioned, there will be 50 to 200 billion connected devices, and 90% of the cars will be connected by then. And there will be close to 200 million wearable devices by 2019. So this leads to the problem of checking nodes in a network. Specifically, we are interested in checking inferential nodes in a dynamic network. Well, we all know real networks are dynamic. I just gave you some numbers. I hope you are convinced. And in a network, the inference of a user is important. What's the inference? The inference, by intuition, is just the popularity of, for example, the user's tweets. And why do we want inference users? Yeah, just give you one very simple example. You see it many, many times. Is cold start recommendation. Well, in a social media or social network, you have some new users, and you want to recommend something to the new users. What do you want? You don't have any background information about this user. So a bit is that you may say, I give the user some influential users to get popular tweets as soon as possible, okay? And some people, if you do not work on this area in the past, you may heard something like inferential maximization in the past. You say, hey, is this just an inference maximization problem? Well, it's related but different. Different in the following sense. In inference maximization, you are trying to get a set of nodes so that the combined inference of that set of nodes is maximized. In other words, you hold one assumption, is that the inference propagation in the inference maximization problem is somewhat synchronized. Synchronized meaning they are promoting the same thing. However, in real social media and social networks, different people may have different opinions and may have different message to spread. They are not synchronized. They may talk about completely different things. So each influential user posts her own tweets independently. So just a little bit technical background. So what are the propagation models? Okay, and typically what we do is that we will have an inference network, and for each edge, we have a weight, which is its inference weight. The bigger the weight, the more likely this node is influenced, V is influenced by U. Okay. And we say a user V is a city user if this V is activated and times 0, or we say V starts as a propagation. And what we are interested in is IV, the inference of the node V, which is the expected number of users who are activated in the propagation started by V. In many applications, we use one of the two very popular inference propagation models. One is called linear threshold model. Linear threshold model essentially says, well, we have a node V, and it chooses a random threshold independently from the other nodes, okay? And it looks at its neighbors. If the combination of the inference from its neighbor is over this threshold, then this node becomes activated. Well, very intuitive idea. So, for example, this is the linear threshold model. This is V. It looks at its neighbors, and then it sums up the inference of its neighbor and decide and compare the total of inference with its threshold. If it is over the threshold, then it is motivated. Otherwise, it is not. Okay. Another idea is the independent cascade model. The idea here is that the intuition is that, well, for each node at time t, this U has a chance to activate its inactive neighbors by a probability. Okay, so this is the probability of the edge, and then we also calculate the expectation of number of nodes in the network that this seed node can activate. And it has been shown that computing this expectation itself is a sharply hard problem. That's even P equals NP, the sharply hard problem still doesn't allow a polynomial time algorithm to solve. So it is really a challenging problem. Okay. So we can always turn these two models into some equivalent live edge process. Okay. So this is an example. We have this node V, and then we can change it to live edge. Okay. So we have a large graph, millions or billions of nodes. We want to estimate the influence of a node quickly. And of course, if you have to compute everything from scratch, you have to do simulation or similar things, then it will be very time consuming. And if you want to track the inference in a dynamic network, this is infeasible. So one idea people may think about is, well, whether we can use some sampling techniques to estimate. This is a very typical thinking, very natural thinking in tracking dynamic behavior, right? The challenge here is that sampling in a network is quite different from sampling from, for example, a set of numbers. The reason is, in a network, the nodes are connected. If you only sample nodes independently, you cannot capture the association, the correlation among nodes. And you may not even get a connected graphs. And the sample itself may not give you anything about the measure you want to estimate. So we need to come up with a better way to do sampling. And recently, in the last 2 or 3 years, and people start to use pooling to do the estimation of inference, or indeed its general measurements on networks a lot. And the idea is beautiful and simple. So what does pooling do? Okay, pooling is essentially try to pool a reversely reachable set. The process is very simple. We randomly pick a node, Z, let's say, and then we run the live edge process, and we return the set of RR set of nodes, then can reach Z via those live edge as a sample unit. We do this again and again, so we accumulate a sufficiently large number of sample units to form my sample, and then we estimate the measures according to that. I will tell you some details later, but the general framework is just that simple. Okay. So mathematically, one important property here is that, well, if you have these M samples, M independent RR sets, then the number of, then the expectation of the inference V can be estimated by the estimation of this N, which is the number of nodes, times the dV, which is the RR set containing this V, divided by the sample size. Okay. So let me show you the process, how to get a pooling sample. You randomly pick a node, and then you look at what are the other nodes that may propagate the inference to this node, okay? And then you, if you use a linear threshold model, you just flip the coin to select a path, okay? And then this is your sample. It's your sample unit. And then you start from another node randomly and do this process again, get another unit, okay? If you use the independence Cascade model, then you look at all its ancestors in the network. So we have the observations here are RR set under the LT model is indeed a random path, and RR set under the IC model is a random connected component. Okay. Now, so far so good. Those are the things done in the last 2 or 3 years by others. Okay, not by us. So now we tackle the problem we want to do here is how we can do the dynamic inference networks. First of all, how should we model a dynamic network? We can model the dynamics on network as a stream of edge weight updates. Because at the very beginning, you can assume all the nodes are already created by the God, already exist, but they are not connected. As long as they are not connected, they won't have any effect on your inference calculation, right? Everything is isolated. So whenever a node is connected, then how can you see a node is connected is the weight changes from 0 to something, right? So to that extent, the edge weight update can be used to model the change is that we can have the edge weight updates, u, v, which is an edge, and we can have a sign to signify whether this is increase or decrease of weight. And delta is the magnitude of the change, and t is the timestamp. So to this extent, this is a stream related to the temporal information, but it is not really a traditional time series. Okay. So how can we update the R set against the edge weight updates? Because, well, as I explained to you, if you maintain a good R set, indeed, estimating the inference becomes really simple. You just calculate the expectation. And calculating the expectation, you only need to count for how many R sets contain this vertex V, right? And then by simple calculation, you can get the expectation. But the real challenge is how can I maintain the RR set sample? Okay, so when the network updates, indeed, we do not need to redraw all the RR sets. We only need to update those RR sets affected by the changes. Okay, so if if an update only affects the live edge pointing to V under both the LT and IC model, and we update it, otherwise we just keep it. And to update it, the idea is that we can use the reservoir sampling. In the LT model, we just repeat the live edge pointing to V according to the new probability. Because you change the weight, you change the corresponding probability. Okay. For the IC model, because you change the weight, then you make the edge UV live or dead according to this new probability. And we find all those nodes reach the Z via those live edge. That's all. Okay. And once you have maintained these R set, and then you can calculate the inference nodes as follows. You just return all the nodes with high degree in the maintained R set, and then you can return them. The algorithm is extremely simple. But wait a minute, there's one thing. We have a parameter m, which is the number of sample units we should use to get good estimation, to get accurate estimation. What should be the number of m? Okay, and also when the graph changes, this m may also change because the underlying graph structure changes, right? So this is indeed the critical problem. How many R sets do we need? So the goal is that, well, we want to estimate this m, but due to the Sharpe harness of the computing this L, the efficient exact extraction of the inferential nodes is unlikely to happen. So what we really want here is that we want to have a high recall. Indeed, it's 100% recall with high probability. And we want to constrain the error of false positive nodes to a range specified by user. Okay. So what we can do is that we retrieve all the R sets affected by the edge weight. We update those R sets, and we add or delete these R sets if the current sample size m is proper. And to decide the R set size m, we use the martingale inequalities here, which will give us the probability, the quality guarantee in the probability sense. Okay. So if you follow this mathematical model, you can decide the sample size according to those formulas. Okay. So that's the basic framework to solve the problem. And Well, when we use a threshold-based checking, meaning I want to retrieve all the inference nodes whose inference is over a threshold, indeed the previous model works nicely. However, if you want to do the top K checking, things is a little bit tricky because we do not know the threshold value IK. So what we can do is that we can first bound this IK using a sample set, and then we apply the method of threshold-based checking for finding the inference nodes, and we approach the top K list here. Probably I can skip a little bit details here. Oh, sorry. So another thing is that we need to maintain those node ranking. We have a data structure so that it can achieve constant time retrieval for each node. So that means you don't really need to do, for example, binary search to find the node and its corresponding you can do it in a constant time. That guarantees that the whole processing time is constant per node. Okay. So we conduct experiments on pretty large graphs, and then we partition the graphs according into three parts. One part is as the initial graph, and the second part as the edge that will have the weight increase, and the third part as the weight decrease. Okay, and we verify that the quality guarantee indeed. One tricky thing here is that we do not really have the absolute ground truth. The reason is that in order to estimate the inference, you have to do simulation. And then the simulation, it will converge mathematically, but in practice, it never really converge, right? You're always in a small range. Particularly if you want the top K list, the top K list may change quite substantially with a very minor change of the value, right? Because you are not looking at the inference value, you're looking at the relative order of those entities. So that's the reason why we have to, we only have sort of like a pseudo ground truth. Okay. So, this is the result. As you can see, we compare the simulation result and our algorithm result and see how the top K lists are similar to each other, meaning their inference values are close to each other. And you can see they are pretty similar to each other. That means the results from the sampling approach indeed is of quite good quality. And in terms of scalability, you can see that the value here, our results is pretty, scalable, meaning the number of updates, with respect to the number of updates, our performance is almost like a linear. Okay, for the linear threshold model. For the IC model is not that well, but is still good in a wide range. The reason behind this is very simple, because in linear threshold model, each RR set is a pass, so it's a linear processing. But in the IC model, each RR set is a dynamic subgraph, right? So you may have branch so that it may incur more cost. Okay, this is still an ongoing work. We are still working on how to control the retrieve error in the top K checking task and how to do the inference maximization on dynamic networks. Okay. Well, related to this, we also work on something like viral marketing in the say more application scenarios. Okay. For viral marketing, the general setting is that, well, we will provide user free products. This is an implicit assumption. If a user is offered a free product, the user will adopt the product and propagate the words. The idea here is that, well, whether this assumption holds or not. Let me ask you a question. How many people here switch from iPhone to Android phone? Very few, right? How many people here use iPhone? Okay. You know what I want to say, right? Well, if I simply offer you a free Android phone and ask you to switch from iPhone to Android phone, many people, no, I may not want to do that, right? In other words, I give you a free product. You may not be simply becoming an adopter. Okay? So this assumption may not work. So a better strategy is, instead of giving a free product, let's give you some discount. Give discount serves two purposes. The first is that it's a test of your willingness to switch. Okay, if you are not interested in switch anyway, even I say I give you a new Android phone for $50, you say still $50 because anyway I won't switch. I don't want it. So you save a new Android phone as your test. But if you are you're seriously interested in considering the new product, $50 for new phone, well, it's a good deal. Why not? Then you'll use it. So this will be an indicator or filter of those users not going to be adopters. This is the first thing. The second thing is that we can use discounts to compensate the user's influence, the user's status in the social network. For users who are more influential, we can give them deeper discount. For users that who are not that influential, we give them less discount. Okay. So the problem now becomes what discount we should offer to the users. Well, this is nothing new in marketing theory. Indeed, if you look at marketing theory, they already established these called purchase probability curves long time ago. Well, the x-axis is the discount rate. The y-axis is the probability a user may adopt the product. And the red line here is the benchmark user. So its inches is linear with respect to the discount rate. But in reality, users are typically either the discount incentive users, which means that, well, you have to give them very deep discount. They will be motivated. Okay? If you only give them very little discount, they won't bother. Okay? Like iPhone users are typical such things. If you say, oh, I just give you some discount, they don't motivate it. If you say, not only I give you a free phone, I will pay you $10,000 every year, probably I will consider that seriously. Okay, so this is a discount incentive. And in the other curve, on top of the linear curve is a discount sensitive. Those users are very sensitive to discount. If you give them a little bit, they will purchase, they will buy. Those iPhone users are very sensitive to discount. You know, Best Buy every Christmas only give $50 off on the new model of iPhone. So many people just rush to Best Buy to buy it, right? So the technical problem is that if we know the a continuously differentiable function that can the model the user's purchase probability. And well, of course, we assume this probability is monotonic. But in reality, it doesn't have to be monotonic. But for the sake of simplicity, let's assume that. Okay? Most of the time, they do. And then we want to compute for every user what's the customized or personalized discount rate I should offer, so that I can maximize the total amount of influence in the network. Well, if you only pose this problem, of course, a trivial solution is that you give everyone a free product. That will give you the maximization. So we need a budget to constrain that. So we have a safe budget here, meaning even if everyone cash the discount rate, I mean, even if everyone takes the discount, I still within this budget. So this is a safe budget. So if you model the problem, indeed, what we get here is we call the continuous inference maximization. It is a generalization of the conventional discrete inference maximization. Because in the traditional model, you either give a product for free or don't give any discount, right? But in the new model, we allow a discount rate for everyone. Okay. So this problem can be done using a coordinate distant net framework. I won't go into the technical details here because it's close to lunchtime, and then I know many people here got up very early in your local time. So, but if you are interested, please you can check out our Sycamore paper last year. And then we also have the source code available on the web, and our source code has been certified by Sycamore as repeatable open software. Meaning Sycamore has the third party to test. They can obtain whatever we claim in our paper independently. Okay. So, Jian mentioned that I would talk about a little bit about my work in Huawei. Well, we academia produce a lot of algorithms on graphs, no matter dynamic graph or static graph. That I have been done with my students in the research group. But we have one problem. We have one challenge. How can we implement such algorithms in scale for the real networks? So we need to build graph engines. And there are many graph computing engines already. And you can see a lot of them here. And more are not included because of the size of the slide. Okay? And the challenge is, why do we have so many different query engines? The challenge is that it is hard to entertain queries, analysis, and visualization at the same time. So people need a different graph engines. Well, this is the performance chart of the Graph 500 competition. Essentially, Graph 500 is a benchmark for graph data processing. Okay, and then different product teams will submit their entries to the competition. Essentially, is that if I have essentially we use different available sources, and then we what's the throughput rate. So that's the linear regression line. The dashed line is the linear regression line there. One thing very interesting to observe here. Well, first of all, here there's no winner and loser, okay? Because different applications have different size, different scale of data, have different computational needs, right? So what you really need is that you find the appropriate size engine to fit your application. If your application is small, you use a huge supercomputing engine, it's waste of the resource. If your application has a lot of data, but you use a tiny engine, then you just cannot catch up with your data. So one thing here interesting is that if you look at the left bottom corner, you can see quite substantially the points go over the regression line, right? Why that? Well, that means within a we know a lot how to make the graph processing engine efficient, so that the performance can over this regression line. And on the right-hand side, the points become sparser and sparser because it involves cluster and supercomputing setting. Okay. And then you can see go over the dashed line becomes more and more difficult. So when we join, when we are in Huawei, one thing we are thinking about do is that can we do a graph engine that we use commercial servers? We don't use any supercomputing facilities. Then we can achieve good performance. That's our design goal. Okay. So essentially, we try to target at the red arrow line at that level, using as little resource as possible. So this is the architecture of the graph engine we built, and it is built on the Huawei Enterprise Cloud, and then the have several levels. We support visualization, analytics, and the user development. Okay, the graph supports property graph representation. Essentially, is that on each edge you can have tags. Each node you can associate it with tags. And we are working on the next version. Is that even for the nodes you can have a database there. Okay. So indeed, within a lot of the work there is not really the algorithm work. Instead, it's the engineering work. And we use, for example, very simple, but I still call it smart methods to divide the data into shards so that we can balance the servers, and that allows fault tolerance and redundancy for efficient processing. Okay. So let me show you some results we just got a few weeks ago. We use a cluster of 9 machines, each with 44 CPU at least 2.6 gigahertz, and each computer has 128 gig shared main memory for this graph engine. You can see it's really affordable server configuration. It's not supercomputing servers. Okay. And in our experiments, we observed that the memory cost is just about 90 gigabyte main memory. And the data set is we use the Fraser synthetic data graph generator to generate a graph of, say, close to 1 billion vertices and have over 100 billion edges. So we call this graph is a large graph. Okay. And then if you put the graph into binary data, is close to 400 gig data. So you cannot put this data into any single machine completely. Okay. And what we do is a 3-hop neighborhood search. Essentially, is randomly pick a node and return all the nodes within 3 hops from this node. Okay, if there is a path, say, I have a node Q. If a path between V and Q, say Q, V1, V2, V, then this V should be in. So we retrieve all the things. Why we do this query? Because because many queries in the graph involves the path search. Right? If you think about what we did in the pooling process, essentially you just look at the neighbors, and neighbors, right? So that is the reason we use this as a benchmark query. Now, this is the result. There's everything interesting. The first is that, by the way, we run the 100 concurrent queries, meaning we produce a large number of queries to feed the servers. And in the servers, we maintain 100 threads to actively take queries. So at any time, anytime meaning during the time we are doing the testing, there are 100 concurrent threads taking queries. So there are 100 queries concurrently running. So if you look at this thing, we can see a large number, over 80% of the queries can be answered within 1 second. So this, I want to remind you, this graph has more than 100 billion edges. So if you want to retrieve, query 3-hop neighbors within 1 second, this is, to the best of our knowledge, this is the fastest one in any publicly announced results so far. Okay, and there's some more difficult queries. Why they're difficult? Because the data, the nodes just cross the border, so they need to read the data from different shards. But even that, all the queries can be done within 4 seconds. And on average, all can be done in 3 seconds. So this is a pretty pretty good result. We are very excited about that, and we are working more along the line, including, for example, using the techniques to support visualization, and including to support the user development. Yeah. So this will be publicly available for testing very soon. It essentially is later this year we will announce the product. This is pretty much I want to share with you today. Yeah, thank you very much for having here. I'm pleased to take any comments, suggestions, and questions. Thank you.